Welcome back to another Signals and Systems video. This one we're going to focus on continuous time Fourier series properties. Before we get into the specifics of the properties, one is these properties we use to allow us to look at a function and make some statements about its Fourier series coefficient without having to calculate it. And then the reverse is also true. We can literally take a look at some Fourier series coefficients of a function and be able to tell what that function is, what are the properties of that function. I mean, looking at this, for example, if you look at the first one, it says if you were to have Fourier series coefficient of a signal, and if that signal's Fourier coefficient of that signal was a of k, then that a of k was equal to a of minus k conjugated. By definition, that means that x of t is real. Okay, and so that's what it says. And also the reverse is true. If x of t is real, then this will be conjugate. If you haven't come across conjugate before, that conjugate simply means replace everywhere you see a j, replace it with minus j. So basically, if I've got a complex number 2 plus j3, I'm simply going to write it as 2 minus j3. So wherever you see a j, replace it with minus j. That's all a conjugate is. Okay, nothing more. So it tells a property, so I can look at the Fourier series coefficient and say something about x of t. Now another important feature of this is if I happen to have a Fourier series for a function of x of t, I can actually use it to figure out the Fourier series coefficient for a function that is similar to that function. Maybe a derivative of it hasn't been taken, so if it's a derivative of the function I already have, I just multiply a of k by jk omega 0 and I'm good to go. And then, for example, if it was shifted in frequency, then I just multiply it by e to the jq omega 0 t, where q is the shift. And if it's a derivative, if it's an integral, then I divide it by jk. And you can kind of see if it's a linear system, I'm just simply going to add the pieces together. If it's a multiplication, it becomes a convolution in the other domain. Oh, and I jumped over here. If you've got a convolution in time domain, it's just simply a multiplication of the Fourier coefficients. Okay. Now, some of the other properties don't look as promising, but they are very, very important. One is this Parseval's relationship, which basically says average power of the system, whether you measure it in time, as you've done in a period here, or you measure its coefficients, it's going to be exactly the same. So it doesn't matter whether you're calculating average power in frequency, or you're calculating average power in time domain, your answer is going to be the same. Some of the other properties that are useful is like if your x of t is real and even, your a of k is real and even. If your signal is real and odd, then a of k is purely imaginary and odd. Time reversal gives you adds a negative to the k for you on the other side, so it flips if you flip your function, you're going to flip the other function. So time reversal causes a frequency reversal, and time scaling really does not impact a of k, and then time shifting just adds the e to the jk omega 0 t0 to this. So these are the properties, and those are the uses of the property as we've talked about it. Now, I'm not going to provide the proof in these videos. The proofs are available in a number of sources, and I would encourage you, at least for a few of them, if not all of them, either try to prove it for yourself using the analysis and synthesis equations of the Fourier series, or go look at a resource such as Oppenheim or the textbook we have that which is attached to these videos to get the proof. Okay, so now the next question is, so let's take a look at an example of using this. Let's say you've got a situation where you are given an x of t, and this x of t is supposed to be real function, and with a fundamental frequency of, let's say, 100 pi radians per second. Okay, and so that's given. The other thing they've given us is that the non-zero coefficient, Fourier series coefficient, are a minus 1 equal to 2, a0 equal to 5. Now you've got to be really careful. Just because it says these are the 9-0 doesn't mean everything else that is not explicitly given here is 0. You got to be careful, because if they gave you a property and that property leads you into another non-zero coefficient, you have to pay attention to it. So for example, here, because they said it was real, the x of t was real, if you go back to the properties and look up here, if x of t is real, then what does that mean? That means that a of k is equal to minus a of k. So you say, okay, if a of k is equal to a minus k conjugate because of the real, and they've given a minus 1, that means I'm going to have an a1 that equals to a minus 1 conjugate. Okay? In this case, when I look at this thing, we say, okay, is 2 is real, so there's no j to reverse, so that's going to be 2. So even though they had not explicitly given me a1 was given through this, and this through a combination of this, they've given me a1. So in this case, in reality, not only I have a minus 1, I also have a1 equal to 2. So that's one thing. Now let's say they come back and say, okay, find xt plus 5. Find xt plus 5. Okay, so if that's fine, well, one is I obviously have to find x of t first before I can do anything else. So I'm going to say, okay, I know x of t, I have the Fourier series for x of t, so I can say x of t is equal to the summation of k going from minus infinity to infinity, a of k e to the j k omega 0 t. So j k omega 0 t. Pretty easy. So I've got a few a of k's, on the only ones that k, so I'm gonna have one term for k minus 1, one term for k equal to 0, and one term for k equal to 1. So let's take a look at k is minus 1. The coefficient is 2, e to the j, k is minus 1, omega 0 is 100 pi, and t. Okay, and then plus this one, k is 0, so it will be 2 e to the 0, which is 1, plus 2 e to the j 1, because k is equal to 1, 100 pi t. Okay, which if I clean it up a little bit, I will have 2 e to the minus j 100 pi t plus 2 plus 2 e to the j 100 pi t. Now I can get a little fancy and say, well, I know Euler can put these two together, and that'll become 4 cosine of 100 pi t plus 2. Okay. I'm sorry, this is a 5, I believe. Yeah, a0 is 5, so I got carried away with all the 2's. Plus 5. So it's a sinusoidal signal with a magnitude of 4, and then you have a DC component. This is your DC component of 5. Okay, all right. So that looks good, and of course, if you have a chance, you can draw this and kind of see what it looked like. Now let's say they come back and say, that's great, but what is xt plus 5? That's easy, right? If I have x of t, then xt plus 5 simply would be, just take the t and replace 5 with t plus 5. So it would be cosine of 100 pi t plus 5 plus 5. Pretty straightforward. So that. Now, let's say they come back and say, okay, now that you found that, why don't you find a of k's, let's call them b of k, just to distinguish them from a of k. B of k's, which are the Fourier series, which is the Fourier series coefficient for x of t plus 5. So, well, I could, of course, use the analysis equation, plug in x of t plus 5 to go find it. That takes a little bit of work. But I say, wait a minute, I have a of k's, which are the Fourier series coefficient of x of t. Is there any way I could find, if I have a of k for x of t, is there any way I could find b of k's which belongs to t plus 5? So what you do, you go back up here and take a look at that and say, oh, first thing I see is time shifting. That's what it is. It's a time shifter where t0 is equal to minus 5. I put that up there. Time minus 5, because this is xt minus t0, we have t plus 5. So t0 is minus 5. So it's okay, therefore I can take advantage of this equation, which basically says that my b of k would be e to the minus j k omega 0. Actually, this is omega 0, which is 100 pi, right, times t0, which in the case is minus 5, as we saw. Okay, so times a of k. That's great. So what can I do? Well, I can say, okay, if we got this, then we know b of k is simply gonna be whatever a of k is times e, and we're gonna clean this up. So we got minus and minus becomes plus, so it's gonna be jk 500 pi t. jk 500 pi, and that's it. Okay, so we're almost there. So we're basically taking advantage of this property instead of having to go through the whole process of redoing it. And so that becomes pretty simple. That means that b of k only going to have b of minus 1, which is going to be 2e to the, oops, k is minus 1 for this one, so it's going to be minus j 500 pi. For b1, it's going to be 2e to the j 500 pi. And for b0, the DC one is going to be, since k is equal to 0, it's still going to be 5 and nothing attached to it. So you can see that, you know, we can use the property to figure out what the, from frequency side, figure out what the time domain is, or from time domain, figure out what the frequency domain is. The other advantage is we can use the properties to leverage what the Fourier series we know to find the Fourier series for the functions we are looking for. That brings us to the end of this video talking about continuous time Fourier series properties, and that's it for this video.